Hello everyone. Today we will see lab program 9 of design analysis of algorithms laboratory. The aim of the program here is to find the minimum cost spanning tree of a given undirected graph using Prim's algorithm, and we have to now implement the same program, the same algorithm and the program in a Java language. So before we go for the program explanation, we'll have to now two aspects of the program. One is the representation of a weighted graph and how exactly the Prim's algorithm work in order to find the minimum cost spanning tree followed with the program. So the representation of a weighted graph. So for Prim's, the input is a weighted graph, right? So when we have a graph, which is now a weighted graph, how do we represent it and how the same representation is done in a program? We'll just look into it. So what is a weighted graph before to that? Is a graph where each of the edge is associated with a weight. And also here, the weighted graph, if we have, it is represented by cost efficiency matrix, which is of size n cross n, where n is the number of vertices. So if I name the weighted graph as W, then every entry in the matrix W will be either 0, the weight, or infinity. So there are three values in the weighted graph, cost adjacency matrix of the weighted graph. So let us now see when are these three values to be entered. The W of ij will be now equal to 0 for no self loops. So a self loop is a edge where the source and the destination vertex are the same. The W of ij entry is equal to W, wherein W is nothing but the weight if there is a edge from I to j. So if there is a edge from I to j, I write weight of its associated, weight which is associated with respect to the edge I comma j. And if there is no edge from I to j, I write infinity. So as an example, if I take this as my weighted graph, right, the respective representation goes like this. So n cross n. So where n is what? The number of vertices. So I'll name the rows with the vertices and also the columns with the vertices A, B, C, D and A, B, C, D. Respectively, I'll enter the values based on my constraints which have been defined here. So I write 0 for no self loop, weight if there is a edge, infinity if there is no edge. We can begin here. You can see here A to A. I should have an edge from A to A like this. So there's no edge, so I put 0. A to A is now 0. Similar wise, B to B is 0, C to C is 0, and D to D is also 0. If there is an edge, write its adjacency matrix. So, sorry, if there is an edge, write its weight associated. You can see now with respect to A, there is an edge only from A to C whose weight is 3. For A to C, write 3. And I don't have edge from A to B and A to D, so I write infinity. Is that clear? And similar wise now, with respect to the vertex B, we can now see there is an edge from B to A, yes, whose weight is 2. And there's no edge from B to C as well as B to D, which I write it as infinity. Similarly, with respect to C, I can see that there's an edge from C to B, then C to D, whose weights are 7 and 1. So I write 7 and 1. C to C is 0 and C to A is infinity. Similarly, we can see with D, D to A, there is an edge whose weight is 6. I write 6. D to B, there is no edge. D to C, there is no edge. So I put infinity. D to D is a self loop. No self loop, put 0. This is how we represent a weighted graph using a cost adjacency matrix, or sometimes we also call as weight matrix. So if I have to represent this in my program, so I'll have to represent using a 2D array, right? 2-dimensional array, which now represents my cost adjacency matrix in my program. So 2D array, you all know that arrays are being accessed by using the index, right? So we cannot write now the row numbering as ABCD or the column numbering as ABCD. We write the corresponding numbers, right? So the vertices number, instead of A, I'll write 1 because the index for this matrix is now 1. I cannot write A, isn't it? So A array is indexed by integers. So 1, 2, 3, 4 numbers are given for the rows, similarly the columns. And you can also note here some difference with respect to this and this. So I cannot write this, or I don't have any key in my keyboard to type infinity. So what should I write? Instead of infinity, I myself in the program should designate a large value that does not appear in my cost adjacency matrix, right? And identify such large value as infinity. So I just make sure that 999 does not appear in my adjacency matrix. So I just designate 999 represents infinity. You can use any value, some large value. You can also use 100. Make sure that 100 does not act as weight here. So I'll take a large value here. The large value which I have taken is 999. Sometimes you can also take 4 nines, right? Depends on the programmer, right? When he writes. So this is how we now write the 2D array representing the cost adjacency matrix in a program. So you have to number the indices with now numbers, right? The rows and the columns to be done with numbers, right? So 1, 2, 3, 4 and 1, 2, 3. Fine. Now, what is the task or what is the motto or what is the output of the Prim's algorithm? The Prim's algorithm is basically designed to find minimum cost spanning tree of a graph. Before we go for minimum cost spanning tree, let me tell you what is a spanning tree. A spanning tree T for any graph G which has got V comma E. What is V comma E? V is a set of vertices, E is a set of edges, right? E is nothing but again a graph wherein we name it as T, the spanning tree, which is equal to V dash comma E dash is certain properties. What are the properties for a spanning tree? You can know, sir. It also has vertices and edges. No harm. It is again a graph. Basically, I can tell spanning tree is a subgraph of my original graph with certain properties. What are the properties here? We can see V dash is nothing but V. So what does it mean? V dash is nothing but V. It means that number of vertices in the spanning tree is same as my original graph vertices. The vertices in my spanning tree is same as that of my original graph vertices. And the edges that I now consider will be 1 less than the vertices in my spanning tree. It should be 1 less than the number of vertices in the spanning tree, right? 1 less than the number of vertices in the spanning tree. So remember, the number of edges should be 1 less than the number of vertices. So for example, your graph has 5 vertices. Number of edges should be 5 minus 1, 4 edges in the spanning tree. 5 vertices, you have all the vertices, 5 vertices. Number of edges is 1 less than the vertices. And the graph T should be a connected one and the graph T should be an acyclic one. It means to say that there is no cycle in the graph, right? In the spanning tree, no cycle should be present. It's an acyclic one. So what is this now minimum cost to spanning tree? The next, a minimum cost spanning tree for any graph G is a spanning tree of the smallest weight. So for a graph, there can be k number of spanning trees, right? Out of which I should select one spanning tree which has got the smallest weight. So where the weight of the tree is defined as what? The smallest, when I tell, it is nothing but the sum of the weights of all its edges, right? So this is the minimum cost spanning tree which has got the least weight. So my task of Prim's algorithm is to find the minimum cost spanning tree. And you should remember, Prim's algorithm uses the approach of design, which approach it uses is, it uses the greedy method, which is one of the algorithm design approach. So in greedy method, we know that there are two solutions. One is feasible and the optimal. And this minimum cost spanning tree is now the optimal solution for me, which is obtained by the Prim's algorithm. All spanning trees that I get for a graph is the feasible solution. One which has got the smallest weight is my optimal solution. So the task of the task of the Prim's algorithm is to find minimum cost spanning tree of a given graph. So let us now see some graph is given to us. You can now see T1, T2, T3. They are all the spanning trees. You can now see the graph. Original graph has how many vertices? 4 vertices, A, B, C, D. So all your spanning tree has got 4 vertices. How many edges should the spanning tree contain? It should contain 4 minus 1 edges. That means 3 edges. You can see now I've constructed few spanning trees here. This is one of the spanning tree. This is another spanning tree. This is also another spanning tree. You can see all the spanning trees are connected and they are acyclic. I don't find any cycles here, right? So out of all these spanning trees, I should now select the minimum cost spanning tree, which has got the least weight. You can now see the weight which has been calculated. Sum of all the weights of the edges. 1 plus 2 plus 3 is 6. 1 plus 5 plus 3 is 9. 1 plus 5 plus 2 is 8. So out of which is having the least weight, it is 6. So which is my minimum cost spanning tree for this graph? T1 is my minimum cost spanning tree. So finding the minimum cost spanning tree is now the task of the Prim's algorithm. Let us now see how the Prim's algorithm works. So the Prim's algorithm will basically take the weighted graph, which is represented as V comma E. In program, it is represented as a 2D array. Let us see how it will deal with program in the further slides. Output is now nothing but the ET. What does ET mean? ET is the set of edges which compose the minimum spanning tree of a particular graph. So I should print the edges, right, that compose the minimum cost spanning tree of a graph. So let us begin the algorithm. The algorithm which has already been discussed in your class, you can see that we start with one vertex. So that means to say the tree vertices, the set of tree vertices will be initialized with any vertex of the graph. So start with a vertex, initialize with a vertex, and the set of the edges initially of a MST, that is minimum spanning tree, is empty. Right now it is empty, it's null. So I keep on adding the edge, also keep on adding the vertex into my graph, right? That is VT gets updated with a new vertex, ET gets updated with an edge. So which edge should I select or which vertex should I select is this. So I'll have to find out a minimum weight edge such that we define it as E star is equal to U star comma V star among all the edges U comma V. So I should find out all the edges U comma V such that U is in VT and V is in V minus VT. So what is this VT? So U means is in VT. VT means spanning tree vertices. And V minus VT means the vertices which are not in the spanning tree. The basic logic here is I have to select a edge such that U is in the spanning tree or U is a vertex in the spanning tree and V is a vertex which is not in the spanning tree. So I have to select all such edges. So U is in the spanning tree and V is not in the spanning tree. Select all those edges. Out of the edges, you should select the minimum weight edge and I name it as E star is equal to U star comma V star. And how many times I have to repeat this selection process till I select the number of edges to be equal to 1 less than the vertices. So I'll put this inside a for loop for I less than 1, sorry, for I 1 to cardinality of V minus 1. That is cardinality of V means number of vertices minus 1. So I'll have to do this. So once I select the least cost edge or the minimum weight edge, update my VT. VT is equal to VT union. This is union. So I add V star to my VT because V star is a new edge that comes into my spanning tree. Add V star to VT. Understood? This is union. Why I put union? Because V and E are sets, set of edges, set of vertices. And ET is now ET union E star. So what is E star? E star is my new edge which is selected. So repeat this process till you select the required number of edges, where the required number of edges is 1 less than the vertices. Finally, when I select the required number of edges, return the set of edges that compose the minimum cost spanning tree. That's the end of the algorithm. So the program is basically based on this logic. So selecting a edge which is a least cost edge such that U star is in the spanning tree, is a vertex in the spanning tree, and V star is a vertex which is not there in the spanning tree. Keep updating the vertices as well as the edges of the spanning tree. Fine. Let us look at the program quickly. The program now consists of 2 classes here. So the 2 classes goes something like this. The first class is class Prim's algo, and the other class is the main class, public class PGM9. Right? So first I'll define what is Prim's algo class. It is a class which is dealing with reading the adjacency matrix and finding the minimum cost spanning tree. Right? So this is a class basically defined to work on Prims only. Okay. So let us see what are the what is the members of this particular class. The first data member int n. So here n indicates the number of vertices. And as I said, to represent a graph in the program, I need a 2D array. So the array that I have named is A, which is a 2D array, and the size of the array is 10 cross 10. So you can give anything, but I have just defined it as 10 cross 10. So you can also make it user interactive. So just to avoid all those things, I've just defined it as of size 10 cross 10. Right? There are 2 methods here you can see. One is the read adjacency matrix method. The other one is the find minimum spanning tree method. So both returns void, you can see here. Both are returning void. So what is this read adjacency matrix doing? It is having a code for reading the cost adjacency matrix of a graph, and find minimum spanning tree is a method which is used for finding as well as printing the minimum cost spanning tree of the graph. It will does both the jobs. It will find as well as print. Now, coming to the class of PGM9, which is my main class. It has got a main method, public static void main. And I create an object of Prim's algorithm, E, right? And then call the read adjacency matrix method followed with find minimum spanning tree method. Okay. And this is the end of the class PGM9, right? And the above class here is end of the class Prim's algorithm. So next here is to now define both the methods here, the read adjacency matrix as well as the find minimum spanning tree matrix. Let us see how it is. Sorry, find minimum spanning tree method. So I have to define both the methods, read adjacency matrix method as well as the find minimum spanning tree method. Okay, let us see how it has been done. So in the read adjacency matrix, I'll just put one print statement, system.out.println, which is Prim's algorithm, just telling that my program is doing this particular job. First, I'll read from the user the number of nodes using the scanner class object, which I name it as scan. Creating a scanner class object is very important because I'm reading here, reading the adjacency matrix. Then read the value of n. Suppose if I take the example there of previous one, we had 4 vertices. So A, B, C, D, 4 vertices. So n equals to 4. Next, I'll have to now read the cost adjacency matrix. As I said, the cost adjacency matrix is represented as a 2D array. And the name of the 2D array here is A. And as you all know, to read any 2D array, so I'll have to now use 2 for loops, where the first for loop corresponds to the row and the second for loop corresponds to the column. Right? Let us see how it is read. System.out.println, enter the cost adjacency matrix. The first for loop I write in this way: for int I equals to 1, I less than equal to n, I plus plus. As I said, I number the rows using the numbers which start from 1 to n. So you can see here the numbers starts from, the row numbering starts from 1 to n. So I equals to 1, I less than equal to n. Right? So you can also write I equals to 0, I less than n. So due to some conventions that I use in the next the next part of the code or the program, so I made the convention as I start with 1 and end with equals to n. Similar, I'll have to again write another for loop for reading, for iterating over the columns, right? So for j equals to 1, j less than equal to n, j plus plus. System.out.println. So I have already given here, enter the cost adjacency matrix. So you should keep entering the elements of the cost adjacency matrix separated by a space and separated by an enter key if a particular row ends. So separate the columns with a space and separate the rows with a enter key. So we'll see in the program, when I execute the program, how exactly you're supposed to enter. So whatever you enter, place it in A of ij. A of ij is now what? Scan.next. Right? And this iterates over the entire matrix is now being read from the user. So n cross n values to be read. So if it is 4, I should now read 16 values from the user carefully after it. So remember, when you are entering, enter the column values by a space, enter the row values by an enter key. Okay. So this is an example which I have taken as a graph here, the same graph. So how do I enter? So it is, I'll just enter like this. So 0, space 999, space 3, space 999, then give a enter key. 2, 0, 999, space 2, space 0, space 999, space 999, then give an enter key. Similarly, the third row, similarly, the fourth row, I'll enter. This is how you are supposed to enter. Then close the scanner class object and ends the read adjacency matrix. So you are supposed to enter the matrix in this format. So before you start inputting the graph in the terms of matrix, first you should write the corresponding weight matrix appropriately and then start entering. So looking just at the graph, you cannot enter, right? So quick, on a sheet of a paper, you can write the corresponding adjacency matrix for the given graph, whether it is numbered with alphabets or numbers. Don't worry, just make this convention. So A corresponds to the first vertex, B corresponds to the second vertex, C is third, D is fourth. Make that convention and start entering the elements of your cost adjacency matrix. Now, the next is the method find minimum spanning tree. Some variables to be initialized. Let us see what are they. Min. So there's a variable so called as a min. So min is here being used to find the least cost edge such that U belongs to the spanning tree and V does not belong to the spanning tree vertices. Let us see what is that, how it has been used. And I have two variables again, U and V. So you can see U is a source vertex of the edge, which is in the spanning tree, V is a destination vertex which is not in the spanning tree. So I have initialized to 0. U and V are initialized to 0. K equals to 0. I'll tell you what is K. Count equals to 0. So count is nothing but the number of edges being selected for the spanning tree initially. So I'll have to keep track, right? How many edges I have to select. You all know that one less than the vertices, isn't it? So I'll keep a track of counter variable. Cost equals to 0. What is this cost? Cost denotes the minimum cost of the spanning tree encountered, right? Initially it is now 0. You can now see count is 0, cost is 0. And there is something called as K equals to 0. So we'll see what is that K equals to 0. So next I have another array called as visited array. The visited array now is a single dimensional array, which is very important here to identify which are the vertices in the spanning tree, which are not in the spanning tree. So the visited array, you can now see, is of size 10, right? So for my illustration, I've taken only 4 because I have how many vertices? 4 vertices. So 1, 2, 3, 4. So it is, you all know that in Java, so it will be initialized to the default value of integer that is now initialized to 0 while creating. And you can now see visited of 1 equals to 0, visited of 2 equals to 0. 1, 2, 3, 4, they are the index, and also it represents the vertices, both index as well as vertices. Remember, this indicates index as well as the vertices. Even in your adjacency matrix, index as well as the vertices. Remember that. The visited of 1 equals to 0, visited of 2 equals to 0, visited of 3 equals to 0, visited of 4 equals to 0. What does it mean? That right now all the vertices are not visited. Means to say that none of the vertices are in the spanning tree. I have still not included any vertex in the spanning tree. So 0 means it is not in the spanning tree. 1 means it is in the spanning tree. Remember, 0 indicates not in the spanning tree. 1 indicates it is in the spanning tree. So if I write, say, visited of 2, 1. So if the entry is 1, means to say now vertex 2 is in the spanning tree. Right? So with this knowledge, we'll go for the next line of the code. Int t, I have t is a 2-dimensional array. Can you see? T is a 2-dimensional array. Wherein the number of columns is 3. So I have just written t, number of columns is 3. So 0, 1, 2, that's all. 3 columns I have. Number of rows is 10. So I have just taken only 3 rows. Why? Because I need 3 rows for the reason because I need to select only 3 edges. That means to say here, T is a 2D array which stores the edges of the spanning tree, right? Edges. So what do you mean by that edges? Why do I need 3 columns here? So what am I storing with respect to edges? I'm storing U star, V star and its corresponding weight. Means to say source vertex, destination vertex of the edge which is selected along with its cost or along with its weight. So I need only 3 columns to store U star, V star and its weight W. So I need only 3 columns. I have not used more than 3 columns, specifically 3 columns. And I used here for illustration 3 rows because I have 4 vertices. I need only 3 edges. So what are my 3 edges? How do I know? So I should store it somewhere, right? So I use a T array. Next line of statement is visited of 1 equals to 1. So can you see visited of 1 equals to 1? What does it mean? So as we said in the algorithm, we should now start with any arbitrary vertex added into the spanning tree. You can now say visited of 1 equals to 1. So which vertex is now added to the spanning tree? The first vertex. So visited of 1 becomes, which was 0, now becomes 1 here. So it is now added to the spanning tree. Right? So it now becomes 1. So you can now see here, which was 0. Now this becomes 1. So visited of 1 is now 1, not 0 there. Right? Okay. So now after making, so I have just added one vertex to my spanning tree, which is the vertex which I have added 1. Right? I should repeat something, some logic till how many times? Till I select the required number of edges. So where do I keep the required number of edges which are selected? It is in the variable count. So while count not equal to. So what should be the value of count to terminate this loop? Count should be not equal to n minus 1. What is this n now? N is what? Number of vertices. What is the number of edges that I have to select? 1 less than the vertices. So which variable holds the number of vertices? It is the n, which is the number of vertices. So n minus 1. While count not equal to n minus 1, repeat some logic where I keep selecting the required edges. And how do you select the required edges? Your edge should be a least cost weight such that the starting vertex should be in the spanning tree and the ending vertex should not be in the spanning tree. So you should keep this logic in mind and then start selecting the edges. So once I select the required number of edges, so I'll have to print it, right? So we'll see this code later. So let me just think that I have selected the required number of edges. So where is all your edges stored? It is in T array, right? So I'll have to now print this T array, right? So if count equals to n minus 1, so I have terminated the loop. When did I terminate? When count became n is equal to n minus 1. So I'll continue this loop till count is not equal to n minus 1. So when it becomes equals to n minus 1, I'll terminate the loop, come out of the loop. So if count is equal to n minus 1, system.out.println, so I'll print something. What do I print? The edges that I print. The minimum cost spanning tree with the edges is, so I have a formatting statement, okay? Edge slash t placed with weight. So this is a header. First is my edge, next is my weight of that particular edge which is selected. So how do I print? So you can now see I have to print this T array, right? So there should be some index to this T array. So this is the index. What is the index to T array? K. K equals to 0. I initialized here, right? This K acts as an index to my T array. So I'll have to print this T array. So you all know that T array is now made up of only 3 columns. So I need only one for low because I know that it is made up of only 3 columns. I'll have to just iterate over the rows, not the columns, right? So I write the for loop in this way. For, you can see I equals to 0, I less than k. So I starts with 0, I less than k, right? And I plus plus. I'll iterate over the value of k. So where k starts with, initial value starts with 0 and goes till k less than k. System.out.println. So I'll now print t of I of 0, then followed the concatenation operator plus the arrow mark. Why? Because t of first row, first column gives me the first vertex of the first edge selected. Next, T of I1, first row, second column gives me the ending vertex of the edge which is selected. So, arrow mark plus T of I1 plus slash T, I will just put just to separate it, plus T of I2, I of 2. You can now see I of 2 means I am printing ith row, second column which represents the weight. We'll see the output, then you'll be more clear with that, right? So I'll print this. I will traverse the T array. Remember, while traversing the T array, I need to traverse, iterate over the row. Column not required. We know there are only 3 columns, 0, 1, 2. So I'll directly write. And then along with that, I'll also print the cost, the spanning tree which is stored in cost. Then line, just a formatting line there. Else, so there is sometimes where my while loop will not terminate normally. That means to say, before count reaches n minus 1, that is before count becomes equals to n minus n minus 1, the while loop would have got terminated. In that case, why does it terminate? Because it did not find sufficient number of edges. In that case, print a message that else message spanning tree does not exist. In this case, the spanning tree is not present. Okay, so this is the code of minimum spanning tree. So I have to now tell you, I told you about initialization, I told you about printing, but I'll have to now tell how do I select the edges of my spanning tree. The next slide, we'll now see how do we select the edges of the spanning tree. Okay, let us now see how do we now select the edges of the spanning tree in the find minimum spanning tree, which is inside the while loop, right? So I have written while count not equal to n minus 1. So count till it is not equal to n minus 1, I keep repeating this because count gives me the number of edges that are selected and n gives me the number of vertices. So why should I write this? Because we know that the number of edges for the given spanning tree should be 1 less than the number of vertices. So till I reach. So initially now you can see count is equal to 0. So 0 is not equal to n minus 1. What is n? 4. You can see 4 vertices. 4 minus 1, 3. Still it is not equal to 3. It's still 0. So I'll now start selecting the edges. How do I select the edge? You should be very careful. So selecting the edge such a way that first vertex of the edge is in the spanning tree, the source vertex. The ending vertex is not in the spanning tree. Let us see how it is selected. So I have to now select the edge by iterating over the or traversing over the cost adjacency matrix. It's very simple as it is. So I'll have to traverse over the cost adjacency matrix. How do I do it? Right? So how do I traverse it? So I should be very careful while traversing. Why? Because we have used the concept of visited. That means to say vertices which are in the spanning tree and to the vertex which is not in the spanning tree. So both we have to take care. So we should see how it is traversed. So just look at this. For int I equals to 1. So I'll have to traverse the entire adjacency matrix. So I start with I equals to 1 because earlier while reading also I have read as I equals to 1, comma, min is equal to 999. So I have initialized min equals to the large value that I have been used in my adjacency matrix, which is the large value that is 999. I less than equal to n I plus plus. Okay, so I'll have to traverse the adjacency matrix. Definitely I need 2 for loops there. The only thing is I have done initialization of min. Then for int j equals to 1, j less than equal to nj plus plus. So now which row, which column should I traverse? Right, that's important. So you can now say in the next statement, if visited of I equals to 1 and visited of j double equals to 0 and min is greater than e of ij. So that means to say visited of I equals to 1. What do you mean by visited of I? See, if the entry in visited of I equals to 1 means that I is in my spanning tree. If the entry of visited of j equals to 0 means that j is not in the spanning tree. So I represents source vertex of a edge, j represents the end vertex of the edge. So if visited of I equals to 1 and visited of j equals to 0 means to say I have a edge from I to j such that I is in the spanning tree, j is not in the spanning tree. That's what I want. So I cannot take all the entries here, right? And I should, out of such entries, that is ith row visited, jth row not visited. Out of all those entries, I have to find the minimum value. If min is greater than a of ij, update min as a comma a of ij and update u as I, v equals to j. So u and v are the vertices of my selected edge. So it keeps iterating, updates min, u and v if and only if visited of I equals to 1 and visited of j equals to 0. So remember, 1 means I vertex is in the spanning tree. 0 means jth is not in the spanning tree. Let us now iterate over my spanning tree here. So you can observe here that earlier in my program, so I have added first vertex into the spanning tree. So visited of 1 equals to 1. So it is in the previous slide. Visited of 1 is the value 1, meaning to say that the vertex 1 is in the spanning tree. Now, when I am iterating here, you can now see that which vertex is in the spanning tree? The vertex 1 is in the spanning tree. Only vertex 1 is in the spanning tree, right? Vertex 1 is in the spanning tree. So, which row should I consider for selecting the minimum cost edge? First row, right? And which vertex are not in the spanning tree? How do I identify? Visited of I equals to 1. Visited of I, so visited of 1 equals to 1. And visited of j double equals to 0. That means to say jth value, that is the column value, it should not be visited. So which are the entries are now 0? You can observe here. Visited of 2 is 0, visited of 3 is 0, visited of 4 is 0. That means to say the vertices 2, 3, 4 are now not in the spanning tree. They are not in the spanning tree except vertex 1. So this entire, the nested for loops, right? The two for loops will now iterate over which row? First row, because I is my row, right? And the columns 2, 3, 4. So now out of this 2, 3, 4 column of first row, which is the minimum? So it will find out, right? It will come here. Is minimum, what is minimum now? 999. Is 999 greater than E of 1, 2? No. Is 999 greater than E of 1, 3? Yes, because 999 is greater than 3. So it enters, updates the min value as what now? 3, right? The value which was now here, you can now see min which was now 999 gets updated to 3, right? And now updates even u and v. So what is that u and v here? So we have designated that now the shortest length is now of the vertex 3. Okay, so it is of 3, isn't it? So this is my shortest one right now. This is the shortest weight. So I update this with this. So what is u? U is now corresponding to the starting vertex of 3. So what is the starting vertex of 3 here? 1, and then the ending vertex is 3. So u is equal to I. What is I for me? I is 1, v equals to j. What is j for me? 3. So v equals to, u equals to 1, v equals to 3. So I update it in this way. Next, again it goes because I have one more column here, right? Is min. What is min now? 3. Is 3 greater than a of ij, a of 14999? No. So does not update. It terminates the for loop. Why? Because you can see I is equal to 1, fine. But next I becomes 2. You can see that visited of 2 is still now what? 0. So definitely it's an AND operator. First is false, the rest all, the entire answer is false. Short circuiting of logical operators you must be knowing here. So it will terminate. So I becomes 2. No, 2 is still not visited. I becomes 3. 3 is also not visited. I becomes 4. 4 is also still not visited. Visited means say it is not in the spanning tree. Right? So it terminates this for loop. The entire nested for loop will be terminated. Next, is min equals to 999? Is there any possibility that the min did not change in your searching of the least cost edge? When this will happen? When there are no sufficient edges in my graph for the spanning tree. So break out, come out of the while loop. Right? If not so, update K0, T of K0, T of K1, T of K2 with U, V and min. So I'll update now T of K0. What is K initially? You can now see K is 0 here. So updated. So K, T of K0 with U, T of K1 with V, T of K2 with min. So the first edge which is selected is now 1 and then 3. So you can see K 0, 0, 0, 0, 1, 0, 2, 0, 0, 0, 1, 0, 2 and the weight is also 3. Right? The edge is now 1, 3 with the weight 3. Fine. Next is, once I select this edge, you can now observe which vertex should be now added to the spanning tree. 3. Yes. So where is 3 stored? 3 in general here it is stored in V. So what should I make to add it to the spanning tree? Visited of V equals to 1. So visited of V equals to 1. That is visited of 3 will now become 1. Right? So visited of 3 is now 1. So the updated value you can now see visited of 3 is now 1. It was 0 now becomes 1. Similarly, I should update cost. Cost is equal to cost plus min. So which I have written cost plus equals to min. Cost which was now 0. So I should now update it as cost is equal to 0 plus 3. Min is 3. You can see min is 3. That is the least cost edge. So cost 0 plus 3 is 3. Then update K, because K now should point to the next row in my T matrix or the T array. So K now points to 1. K which was 0 now becomes 1. K plus plus. Similarly, update even the count. Why should I update count? Because I have selected one edge, right? So I should update count. If you do not update count, this leads to the infinite looping because while doesn't terminate at all. So when min becomes 999, then it has to terminate. That's all. So it does not terminate. So you should be very careful. Update count, right? Count which was 0 now updates to 1 because one edge is selected for me. Then end of the while there. Again go back. Is count not equal to n minus 1? Is count not equal to n minus 1? Count is now 1, right? But it should not, is it not equal to 4 minus 1? That is 3. So if you can observe here that count is equal to 2. So count is now 1 here. You can observe. So I'll just put it here. 1 is not equal to n minus 1. That is what? 3. Right? Still I have 2 more edges to select it. Is the condition true? Yes. Count 1 is still not equal to 3. Right? 1 is not equal to 3. When it becomes 3, it will terminate. Okay. So now again repeat the same step. So right now, which vertices are in the spanning tree? Can you now see? Visited of 1 is 1, visited of 3 is 1. So which are the edges which are in the spanning tree? 1 and 3. So I should now select which row? First row and the third row. First and third, they are in the spanning tree. Which are the vertices which are not in the spanning tree? 2 and 4. 2 and 4 are not in the spanning. 2 and 4 are not in the spanning tree. So how do I identify that? See, it is still 0. So that means it is not in the spanning tree. Now, so which rows should I consider? First and the third row. And which column should I consider? Second and the fourth column. Because visited of I equals to 1 and visited of j equals to 0. So I corresponds to row. So it should be visited. J corresponds to column. It should not be visited. So in this, you can now see you have only 4 values. 999, 999, and 7 and 1. Out of this, which is the least one, right? You can now see the least one is 1. So min equals to what? 1, right? So min, which was now 3, now will become 1. So let us update it. Min now becomes 1. So u, what is u for 1? You can see it is 3, 3, and v is what? 4. 3 and 4, right? Similar wise, update now the T array. So T array will now, the second edge is selected, whose starting vertex is 3, the ending vertex is 4, and the cost is how much there? 1. Update again. Now the K which was pointing to 1, now points to the next row, that is 2, the index 2. And you should update, very important, is visited array, cost, and count. Otherwise, you may have the chances of leading to infinite loop. So what is visited of V? Visited of V equals to 1. So which vertex should be added to my spanning tree? Fourth vertex. Visited of 4, visited of V equals to 1. Cost to be updated. Cost, which was now 3, 3 plus 1. So you can now see, earlier it was 3, 3 plus 1, 3 plus 1. Now the cost becomes 4, right? Then what is count? Count. So I have done with 2 edges, right? So count gets updated too. Done, right? Again goes back. Now you can see the condition here. Is 2 not equal to 3? Yes, condition is still true. Again enter the nested for loop. Now in the nested for loop, what are the values of I? I, the rows which have to be selected for getting the least cost edge. So which are visited now. 1 is visited, 3 is visited, 4 is visited. So there are 3 rows which are visited now. So this with, right? So 1, 3 and 4 are visited. 2 is not visited yet. So you can see 2 is still not visited. So out of this, right? So which is the minimum one? You have to now identify. Is that clear? So you have to now identify which forms the minimum here. So visited of I equals to 1 and visited of j equals to 0. Very important. That's very important here, right? Visited of I equals to 1 and visited of j equals to 0. Fine. So now, which forms the minimum here? What is the min value? Min value here is which should you consider? The second column, and the rows to be considered here is 1, 3 and the 4, right? So I have to find the min values from 999 from 7 and 999. Okay, you should not consider the second row. Why? Because second is still not visited. Do not consider the second row. You have to consider second column and first, third and fourth row. So out of this, which is now the least one, 999 is not the least. Don't consider this. Second row not to be considered. 7 is the least, right? And this is also 999. So 7 is now the least one. Okay. Similarly now, update min and other things. Let us see how do we do it. So min now becomes what? Min equals to 7. What is u? U is now 3, right? U is 3. V equals to what? 2. Because 7 corresponds to the age 3, 2, right? Now, count now becomes what here? 3. The third edge is selected, right? So now let me update K first. So K equals to 3. I'll update K. K is equal to 3. Now you can see it is now outside the T array right now. It is in third index there. Now, which is the edge which I should add it to the spanning tree here? It is 3 and 2 whose cost is 7, right? So now which vertex is added to my spanning tree? 2 is added where the cost is 7. So what is the updation of cost here? So 4 plus 7, that's equal to 11. So cost becomes 11. Count becomes 3. So I've left this. This is very important. So I should again update this. If I don't update, you will lead to infinite loop. So visited of 2. Why visited of 2? Because V is 2. The next edge which will be added is now 2. So visited of 2 equals to 1. End of the while. The while again repeats. Now you can see count is what now? 3. Is 3 not equal to 3? Is the condition true or false? Now you can see 3 is equal to 3, right? The condition now becomes false. So while terminates and goes back, comes out of the while loop and prints the corresponding edges along with the cost. For this graph, whatever we have considered here, the cost of the spanning tree here is 11, where the edges which are selected are 1, 3 with the cost 3, 3, 4 with the cost 1, and 3, 2 with the cost 7. Right? So let us now see the execution part of this program. So we will now see the execution part of the program for the same graph which we have considered. Enter the number of nodes. Takes some time since I'm using the online compiler. One second. Okay, so the same program which I have told is here. So enter the number of nodes. So you have to enter 4 for the graph. Enter the cost adjacency matrix. So whatever is the cost adjacency matrix, the same matrix I'll be entering. As I said, separate the columns with a space and separate the rows with a enter key. So 3999. Enter. I have to write the next row. Okay, 2 0 999 space 999, then 999 7 0 1, enter 6 space 999 999 space 0. So as per our tracing, my cost adjacency matrix, the cost adjacency matrix is like this. and the spanning tree is of the cost 11 with 3 edges been selected. We can now see the output. The minimum cost spanning tree with edges is equal to the header is printed edge and the weight. You can now see minimum cost spanning tree with along with the edges. The edge is 1 3, which is of weight 3. The next edge is 3 4, which is of the weight 1. Next edge is 3 2, which is of the weight 7. And the cost of the spanning tree is equal to 11 there. Okay, so you can also see that here whatever we had traced, so we've got the same output also. So 1 3, the edge with the weight 3 3 4 1 3 2 7, and the cost of the spanning tree is equal to 11. So due to that online compilers it's been delaying. So normally if you will work on Eclipse or the using Java compiler in your Linux Fedora, it will work fine. So due to that online compiler, it is slightly slow. So otherwise, it is fine. Okay, this is the program and how it works. So you should remember how to enter the cost adjacency matrix. So separate every column with a space and separate every row with a enter. So if you make mistake here, the output will be wrong. So you should be very careful with the same. You can see the cost is 11, 1 3 with cost 3, 3 4 1, 3 2 7. Same output which we had got earlier, right? So the program execution I have just told you. Thank you.